Welcome students to the bridge course of BTech first year. From the screen you can find that we will be discussing about the module 5, which is the modern physics. Actually this particular module consists of two parts. One is the quantum physics, another is the statistical physics. Here in this particular lecture series we will be discussing the quantum physics part. Let us first see the topics of our discussion briefly. First we will be discussing about the introduction to quantum physics, then history of quantum physics, that means how the subject has evolved. Next, comparison between classical and quantum physics, particle and wave nature, principle of complementarity, correspondence principle, de Broglie hypothesis, Heisenberg uncertainty principle, concept of photoelectric effect. These are the main topics of our discussion. Few parts you have already done in class 12, but briefly. Now let us first come to the introduction to quantum physics. Before going into the quantum physics part, first we have studied the classical mechanics. So classical mechanics is intuitive, that means things move in more predictable ways. You have done the classical mechanics part in class 11 and 12, where you have studied the Newton's laws of motion and related phenomena. Now what happens when we move from macroscopic body towards the microscopic one, that means atomic or subatomic level? Here comes the role of quantum mechanics. It provides the theoretical framework which makes it possible to describe with reasonably good accuracy the behavior of radiation and matter at microscopic, that means atomic and subatomic levels. Here the concept of radiation as well as matter both comes in quantum mechanics. We will be discussing in the subsequent classes. Now, to have a brief overview about the difference between classical and quantum physics, let us consider the simple example. An experienced ball player can take a quick look at a fly ball and from its location and its velocity know where to run in order to be there just in time to catch the ball. Of course, a sudden unexpected gust of wind might fool him, but that's only because he didn't take into account all the variables. There is an obvious reason why classical mechanics is intuitive. Humans and animals before them have been using it many times every day for survival, but no one ever used quantum mechanics before the 20th century. Quantum mechanics describes things so small that they are completely beyond the range of human senses. So it stands to reason that we did not evolve an intuition for the quantum world. The only way we can comprehend it is by rewiring our intuitions with abstract mathematics. Fortunately, for some odd reasons, we did evolve the capacity for such rewiring. Ordinarily, we learn classical mechanics first before even attempting quantum mechanics, right? You have done in class 11 and 12 all the parts, basically the classical one, then few parts in the modern physics part in class 12. But quantum physics is much more fundamental than classical physics. As far as we know, quantum mechanics provides an exact description of every physical system, but some things are massive enough that quantum mechanics can be reliably approximated by classical mechanics. That's all that classical mechanics is, an approximation. from a logical point of view, we should learn quantum mechanics or quantum physics first, then come to classical one. By the way, quantum mechanics is technically much easier than classical mechanics. So quantum mechanics can be appreciated to some degree on a purely qualitative level, but mathematics is what brings its beauty into sharp focus. Now we go to the history of quantum mechanics, that means how the subject has evolved. So here is the main important works based on the quantum theory. Towards the end of the 19th century, physicists had started believing that almost all the fundamental laws of nature have been discovered, and as such the main task of physics is just over. Various branches of physics were unified in a general theoretical framework now called the classical physics, and it was felt that all known or to be discovered physical phenomena can be explained in this particular framework. The universe consists of two types of entities, that means matter and radiation, what we have just seen in the previous slide. So matter is made up of localized particles. The classical mechanics, formulated by Newton and further developed by Lagrange, Hamiltonian and many other scientists, successfully explained the motion of material particles subject to various types of forces or constraint. Maxwell developed the electromagnetic theory in 1855, which combined electricity, magnetism and optics in a single framework. He showed that all radiations, including light, are electromagnetic waves. The existence of such waves was confirmed experimentally by Hertz in 1887. All waves shown interference, diffraction phenomena which are well understood theoretically, and you have these particular topics in your class 12 part. During the end of the 19th century and the beginning of the 20th, physicists turned their attention to the study of microscopic structures of matter, the nature of electromagnetic radiation and the interaction of radiation with the matter. In these studies, a number of experimental results were obtained which could not be explained on the basis of classical physics. These puzzling results created a crisis in the theoretical physics. Quantum theory had its origin in the attempts made to explain these results. Radically new concepts were required which were completely incompatible with the classical one. These new concepts are the particle nature of radiation, the wave nature of matter, and the quantization of the physical quantities. The originator of the quantum idea was Max Planck. He introduced the concept of quantization of radiation of energy in 1900 to explain the spectral distribution of radiant energy emitted by a heated black body. Einstein took the next important step in 1905. He used Planck's idea to explain the puzzling feature of photoelectric effect. In 1923, Compton explained the change of wavelength of X-rays when they are structured or scattered by free or weakly bound electrons. The concept is known as Compton effect. The works of Einstein and Compton showed that radiation can behave as particle, thus bringing in wave-particle duality of the radiation. In 1913, Niels Bohr used Planck's quantum hypothesis and gave the first successful theory to explain the stability and observed spectrum of hydrogen atom. He introduced the quantization of angular momentum and the concept of quantum jumps. The next major step was taken by de Broglie in 1923. He suggested that, like radiation, matter also has dual nature. That is, there is a wave associated with every material particle. The wave nature of electrons was verified by Davison and Jarmer and independently by G.P. Thomson in 1927. In 1926, Schrödinger discovered the equation of matter waves and thus formulated the wave mechanics, which is one form of quantum mechanics. Simultaneously, another version called matrix mechanics was developed in 1925 by Heisenberg, Born and Jordan. It was later shown that the two versions are equivalent. Wave mechanics is easier to understand. Therefore, the first course in quantum mechanics always starts with this particular version. The wave-particle duality of matter led to a very important principle called the uncertainty principle. You have heard the name, right? It was discovered by Heisenberg in 1927. Much mystery and controversy surrounded this principle from the beginning. However, it is considered to be the fundamental principle of nature and is important for a complete understanding of the microscopic world. In order to reconcile the quantum theory with the classical physics, Bohr formulated the correspondence principle in 1923. This principle serves as guide in the development of quantum theory. It requires that the result of quantum theory must become identical with those of classical physics if the dimension of the system under our consideration tend to approach the dimension of the classical system. So you can understand how the particular subject has evolved from the beginning.